Hello and welcome to a video on analyzing graphs of unfactored polynomials, which are the easiest case of unfactored, which I call case 2, and it's 0, first, and second degree polynomial functions. So for these functions, we don't have to worry about more than one turning point, because second degree can only have at most one turning point, and 0 and first degree don't have any turning points. So that makes it a little bit easier. Often we don't even need a calculator for these. So let's first look at the first function, and we know what this looks like, f of x equals 4. We may as well get a little graph of this. Now we don't need a calculator screen for this graph. It's just a function that is a horizontal line at 4. So this is 4. There's no x-intercepts. And the end behavior just approaches, it doesn't approach anything, it's just the function itself. So when it's not even curved, there's no approaching. So we could say no x-intercepts. We could say a y-intercept is at 4. Let's take a look at what we need here. So here's all of the things in analyzing. So determining the end behavior doesn't so much apply because the function itself is its own end behavior. It's not approaching anything. It's just staying constant. So we would just, end behavior is just the function y equals 4. It's the same function. Okay, so we also have no turning points. So this function is increasing, never, decreasing, never. It has a domain of all real numbers, as all polynomial functions do. It has a range of just 4, just one number. It's not even an interval, just a single number. And there's not much else to say about that function. Let's just make sure we covered everything. We have end behavior, y-intercept, zeros, there aren't any. We don't need to use a calculator for this one. No turning points. We have a sketch, domain, and range, and it's never increasing or decreasing. Okay, we've got that one covered. What about something that's a little bit more complex? How about a first degree? So we know what the graph of this looks like, and once again, we don't need a calculator for that. We know that this has a y-intercept of -7. We'll just put a point down there and a slope of 2. So something like this, and I'll just plot it in a different color. So there's something like the line f of x equals 2x minus 7. And we can figure out the y-intercept we know is at -7. The x-intercept we can find by setting y equal to 0. So we make y equals 0, 2x minus 7, add 7 to both sides, divide by 2, and we have an x-intercept. In this case, it's not about finding factors. It doesn't need to be factored. It's just about solving for x when y is 0, and that's going to be 7 over 2. I'll just put 3.5. Okay, so that's 3.5. This function's increasing over its entire domain, so all real numbers. It's never decreasing, so never. Has a domain of all real numbers, and as this is an odd power function, so as all odd power functions have, this is first degree, that's an odd degree, has a range of all real numbers. Okay, as far as the end behavior, same thing as we said about the 0 degree polynomial. The end behavior just approaches, so end behavior just approaches y equals 2x minus 7 in both directions, because it's not even curved, so it just always is its own end behavior. It's kind of almost too simple. It makes it more complicated, but even to think about end behavior, because it's just a linear. All right, let's look at something a little bit more interesting. Let's look at a factorable second degree polynomial function. So this we know already. We have mastery of parabolas. We can find x-intercepts always, no matter what, and this is going to exemplify this in example 3, but even example 2, it's factorable. We can find the x-intercepts. So we factor this and we get x and x. I need a product of 8 and a sum of -6. How about -4 times -2? That would be our function in factored form. We'd like to see it in factored form. Now this time there is an end behavior model, and so the end behavior would model y equals x squared. That's the first term. We have zeros, so x-intercepts, at both, what makes both of these 0, so that's where x minus 4 equals 0 and where x minus 2 equals 0. So x-intercepts at x equals 4 and x equals 2, and both of these have a multiplicity of 1. Okay, I don't think we need to put this in a graphing calculator. We could and get a quick sketch of it. It just depends on if you'd rather just find the vertex by just doing negative b over 2a, or you'd rather do a calculator, or you'd rather complete the square. There's many ways to do this. So I think I will complete the square. Why not? So we have x squared minus 6x. I'm going to leave space to complete the square. I have a plus 8, and then I need a space to balance it out after I complete the square. Half of the middle term is negative 3, so I'm going to add 9, which means I'm also going to be subtracting 9. And then this polynomial will become x minus 3 squared minus 1. That's my function. So I don't need a calculator now because I have pretty much everything I need. Right here is going to tell me the vertex at 3, 1. The intercepts are at 4 and 2. The y-intercept, here, y-intercept is at 8. Why is that? Because when x equals 0, y equals 8. Okay, a little squeezed in for space here, but we've got everything we need. So let's just plot this. Okay, now since I didn't use a calculator for that, I didn't make it into a rectangle. I didn't put in a rectangle. I did use tick marks, but I still have the same basic information on here. So now I can tell that this function is decreasing from negative infinity to 3. So let's go with our domain, our range, our increasing, and our decreasing. So this is decreasing from negative infinity to 3. Negative infinity to 3. Increasing from 3 to infinity. The domain is all real numbers. And the range goes from negative 1 to infinity. That's the lowest y value. So negative 1 to infinity. What else do we need here? We have the zeros. We don't have the end behavior. Yes, we do. There's the end behavior. There's the zeros. And then the multiplicity. Of course, they cross in both of those zeros because it's just a parabola. Let's see if we're forgetting anything. Let's look at our list. So we've got end behavior, y-intercept, the zeros and the multiplicity. We have a graph. We have the turning point, the one turning point on the graph. We don't need a calculator for this one. We have domain and range, and we have everything. Okay, let's just circle this as part of our analysis. We have the graph as part of our analysis, and that's everything we need. This one, I'm going to just have you guys pause it, try to do the same thing with this one, and then I'll just show you the answer. And we'll talk about it a little bit. Okay, so this time I factored right here, got the two x-intercepts at negative 3/2 and negative 2, each have a multiplicity of 1. Found the end behavior, it's just the first term, this comes from right over here, first term. And then found the y-intercept by making x equal 0, so y-intercept is 6. I put all this information on the graph. This time I decided to get the vertex, I would use negative b over 2a. So negative b over 2a gives us the x-coordinate of the vertex, negative 1.75. For the y-coordinate, which we needed to find f of negative 1.75, which I got negative 0.125. So here is my local min. That's the vertex, negative 1.75, negative 0.125. So we have the graph. We have all the basic information here. And let's just put where it's increasing, decreasing. Let's put domain, range, increasing, and decreasing. So the domain is all real numbers. The range, lowest value is negative 0.125. So the range is from negative 0.125 to infinity. The function is decreasing from negative infinity up to negative 1.75, decreasing. So from negative infinity to negative 1.75. And then it's increasing from negative 1.75 to infinity. Okay, so there's factorable. Now let's look at one that's not factorable. So what do we do when we have a second degree polynomial function that we can't factor? So I'm just going to go ahead and save some time and say, let's say we've tried to factor it, given up on factoring, so we're going to go on and use the quadratic formula. All right, so when we're looking for the zeros, we can't factor it, but we can set it equal to 0. Let's put it in descending order so we can easily see A, B, and C. And so when we use the quadratic formula, we know that we're setting this equal to 0. So we're looking for the real zeros here. When we, let's see, x equals negative b, that's negative 12 plus or minus the square root of b squared minus, b squared is 12 squared minus 4 times a times c, all over 2 times a. All right, so let's make sure that we know the whole thing's under the radical there. Now let's simplify this a bit. So we have negative 12 plus or minus the square root of 144 plus 60, that's 204, all over 2. We're just going to get this as an approximation. We're not going to worry about getting anything exact here. So this is approximately, and I'm just going to put this in the calculator and we'll see what we get. Okay, so when I added the radical, I got the 1.14. When I subtracted the radical and then divided by 2, of course, I got negative 13.14. Now I also put this on the calculator, and here's the window that I chose. Again, this window can be tweaked depending on your personal preference, whatever makes it clear to you. But when I look at the window, it's something like that, and I've got the graph going something like that. And it's not perfect, but it gives us an idea. And this window goes from negative 20 to 10. And the y's go from negative 60 to 10. And our intercepts, we already know this one is 1.14. And when you're looking at your calculator, that should look right. And then this one is at negative 13.14. Negative 13.1 is good enough, really. We're still going to go ahead and use the calculator to find that vertex. Just you could use that. We're just doing it a variety of ways. You really can choose what your preference is, but I'm going to use the calculator to find a local min. Okay, and I found the min at negative 6, negative 51. I left n behavior out of this, so let's go ahead and get the n behavior and the y-intercept. The y-intercept is negative 15. And the n behavior is just that first term, so it just approaches x squared. And increasing, decreasing, so we've got, looking at the graph, we've got a domain of all real numbers, a range that starts at negative 51 and goes up to infinity, including negative 51. We've got a function that's increasing and decreasing, so it's decreasing from negative infinity up to negative 6. And it's increasing from negative 6 to infinity. Okay, let's look at the other one, and we'll write it out, and then you can compare. So you try to do this, so pause the video and see if you can do this other one pretty much the same way. Okay, so not factorable function, so we applied the quadratic formula. This time I got a negative inside the radical, or discriminant that's a negative number, which means there's no real solutions, no x-intercept. So I expect that when I look at the graph, and since I have so little information, I decided to graph this one on the calculator. And so on the calculator, I got a parabola that has a y. Now I also got the y-intercept of 7 and the n behavior based on that first term. But with the y-intercept of 7, and I know that it opens up, what I saw on the calculator made perfect sense. The thing to be careful of is that it almost looks like the vertex is on the y-axis, but it's not. You have to actually find the local min on the calculator, and you'll see that it's a little bit off-center from the y-axis, and it's at 0.14, 6.8. So once we have that, we're able to find domain is all real numbers. The range is from 6.8 to infinity. It's increasing. It's increasing from that minimum value, which again is a little bit off. It's more like right here, just a little bit off. My graph is a little bit off, so it's maybe more like that, if that makes sense. Not quite at the axis. And then it's decreasing from 0 to 0.14 on the left side of that point.